Hey there! In this video, I'm going to tell you a little something about Collatz branches. Let's start with the basic image. For the sake of conversation, I'm going to take this and flip it upside down. I do apologize about the upside down numbers, but it's just, for what I'm explaining, it's nicer in this way. Alright, so this is the Collatz tree. What I'd like to point out is that every single node in times 3 plus 1 Collatz space, they all have what I call a right parent. That means if you multiply the node by 2, you arrive at another number directly above it that leads back to the original. But some nodes additionally have a left parent. These things here, I've come to call them orange branching nodes. Those are precisely the numbers, the natural numbers that are 4 mod 6. So every time a number is 4 in mod 6, it's an orange branching node. Additionally, if a number is 0 in mod 3, it's somewhere on one of these trivial branches that never again branch further. And if a number is either 1 or 2 in mod 3, then it's somewhere out here on one of these non-trivial branches. Alright, so let's take a look and see if we can learn anything about the structure of what's going on here. We're going to start at 1. And the first branch isn't really at 16, it's actually at 4 because 4 branches left and arrives back at 1. But just for the moment, ignoring that very different circumstance, the first other branch is at 16. You start at 1, you go 1, 2, 4, 8, 16, and then it branches. Every time we hit a branch, what I want us to do is to quote-unquote beam the right parent activity. So we're going to hit this node 16, and we're going to literally draw into our Python program all of these in a row, like this. So that's the right parent activity for 16. But what's the left parent activity there? The left parent activity at this orange node is it steps once to the left, once to the right, and then creates a new orange branch. When we have that particular kind of behavior, I'm going to call those blue. Steps once to the left, once to the right. How about the next one? The next one goes once to the left and then finds itself on a trivial branch, which beams out to infinity, never again branching further. I'm going to call those red. And the next one? The next one steps once to the left and now twice to the right before forming a new orange branch. I'm going to refer to those as white. For what it's worth, conversationally, blue nodes occur exactly, now we're in mod 18, it's gone up by 3. Blue ones are 16 in mod 18, red ones are 10 in mod 18, and white ones are 4 in mod 18. And it's a rotation. Those 3 colors continue for infinity. Blue, red, white, blue, red, white, blue, red, white, etc. Alright, so to help me study this, I designed, of course, another Collatz program. This one I call ripping apart the tree diagram. And this is my main tool that I use to explore this stuff. So let's try it out. It begins by showing us a graph of the beginning of the Collatz tree. We beam the thing, and it shows us this. Alright, so we can pick which of these orange branching nodes do we want to follow further. Just for kicks, let's follow the second blue one, which we see is at 1024. And this program tells us, well, what kind of activity, which kind of orange node does it spawn? And it looks like it spawns a blue one. You're allowed to explore further in that direction. Now, where on this one do we want to travel further from? Let's try this first white one. That's 10,912. And it shows us that this white one spawns an additional white node. We'll beam that one. Continuing the pattern, let's go with the second blue one. So basically, I'm just somewhat arbitrarily exploring. Just this program lets you see what is the nature of what's out there. We hit a red one. Let's go with the first white one again. And we see that it spawns a red one. It seems somewhat random. And I've been really studying this, and it's wild that it's actually not quite random. You'll see what I mean soon. Let's take the second blue one, just do another moment or two on this. And then maybe one more. We'll look at the first white one. Alright, so we can see that there's somewhat of a chaotic pattern here, but I'm at least beginning to label the various different types of behavior and trying to make some sense out of this phenomenon. Let's take a closer look at one of the patterns that I've found. Alright, so when you take this first white node here, what kind of behavior do you get out of it? The first white node steps once to the left, twice to the right, and makes a blue node. The second white one here forms a red one, and then after that it forms a white one. So we see that even within the white nodes, the pattern continues to be just like before, blue, red, white. This is blue, red, white, blue, red, white, but now zoomed out on like a meta scale just within the white nodes. Let's take a look at the blue ones and see what happens. The first blue one spawns a red node, the next blue one spawns a blue node, and then finally the third one forms a white one. So before the pattern was blue, red, white, now we see that it is blue, white, red, blue, white, red. So the direction that we're cycling in has switched. So I studied this really carefully, and here's one of my math journals. I think this is like volume 15 or something. So forgive the poor quality of this image, but so this is the original pattern, blue, red, white, blue, red, white. We see that if we follow just the white ones, following just the white ones, I've called, when we have the standard pattern, blue, red, white, I call that pattern. When instead you follow the blue ones and we get blue, white, red, I call that pattern reversed. So if you just follow the white ones, you continue to maintain the pattern. Follow just the white ones, and you once again continue to maintain the pattern. At any point, if you instead follow the blue ones, the pattern switches. And we can see that if you follow the blue ones, the pattern reverses. And follow, I don't know if I have it here, but if you follow just the blue ones, pattern reverses. Follow the blue ones again, and now it's back to the original pattern. So we have here pieces of structure, bits of logic out in this realm. And it took me a long time to make further progress. To be dead honest, the school semester started up again, I was busy and stuff. But a few months later, after really, really diving in there and trying to understand this, I found something fascinating, and I want to offer you the following thought. I began to suggest to myself, instead of just immediately following the blue one to the next blue one to the next blue one or whatever, what if we instead go one step up and then go over to the right a while? So now we're going to go from a blue one. We're looking for those that go from blue to immediately another blue, and then we're going to go over to the right to a white node. And I wanted to ask, so within the ones that look like this, and you can necessarily find them, just it's a particular, what would that be? Something in mod AT times 3 is 54. So if you wanted this thing, you just have to find a particular value in modulo 54, and you can guarantee that its left parent activity will look like this. But when does this one show up? Let's say I specifically want to start at a blue node, have it immediately put out another blue, and I want to then do this interesting structure. Does it show up every 9th, every 27th, every when? And I was startled to begin studying and realize that it never occurs. These are the only 3 options. It either goes white, white, blue, red, or red, blue. It never happens. So what this indicates is that, I'll get back to what this means in a minute, the whole thing is a lot more connected than I would have thought. So with that in mind, I began to realize that when you're only interested in the original 3 colors, red, white, and blue, you can find out. Let's say we have an orange node, and you only want to know about the activity 1 layer up. So unlike what we were doing earlier, let's say we just want to know this layer. To understand, well, which color you are in, you just have to look at the modulo 18 value, and it determines a lot about the nature of the activity there. If you want to know about the activity on the second layer, all you need to know is one more additional piece of info. You need to know about something on layer. You need to basically take your orange node like this, and you need to know one fact to determine what color it is on the bottom layer. And the moment you learn one fact from layer 2, I call this, you instantly know everything else in that layer. The pattern is very complicated, and I don't understand it. It's wild. It's what I call the grand unified pattern. But none of these are additional independent variables. Basically, on layer 1, there's only one independent variable, and once you know that info, you know the rest of layer 1. And even though I can't immediately tell you where all of the pieces on layer 2 are going to be, you only need one piece of info, and everything is dependent on everything else. So basically, if you want to know the activity for 1 layer, you need to know 1 fact. If you want to know the info on 2 layers, you need to know 2 facts. And what's absolutely fascinating is that if you know a single bit of data from the first layer, from the second layer, from the third layer, and then for as many as you want, you need to know n facts to know, to fully determine n layers of this thing. You just need n facts. So with this in mind, there's a fairly involved number theory proof I'm not going to get into, where you can actually, you can, in a sense, if you take an orange node, what I'm trying to do, is I'm trying to name, with a sequence of zeros, ones, and twos, what is the structural behavior there. Let me show you what I mean. Here's what I figured out. So this is one way to do it, and that's a subject of greater complexity and importance that I'm going to get into right now, because there are many alternative ways to do this. What's the best one? Here's one way to do it. Close this. All right, so let's say you take a node. Just for kicks, I'm going to take 16. One way for us to describe what's happening there is to just follow from blue node to blue node. So we're going to take this one here, and we're going to explore that one further. It's going to arrive at some kind of color, and what I want you to do is I want you to follow on that beam until you hit the next blue one, and I want you to count how many steps did it take. Like here, if this one were blue, it would take 0 steps. If this one were blue, it would take 1 step. It took 2 steps. So we're going to call that first number 2. Okay? We're going to explore the first blue one we found. And we see that immediately it spawns another blue one, so the next number is 0. This is a way for us to actually categorize what is this Collatz shape at for the orange branching node at 16. We're ready to beam. All right, and we see that the first one is blue. It forms another blue node, so it looks like our number so far is 2, 0, 0. I actually didn't plan this out, that's interesting. All right, so let's say we go to this first blue node and we look further. This one is red this time. And it's going to take 2 steps, so we have 2, 0, 0, 2. And then finally, let's do one more and see what number we get. We get a white node, and this time we get a 1. Basically, we now have a 1-to-1 correlation between theoretical shapes and structures of Collatz branches and sequences of zeros, ones, and twos. If you follow just the blue trajectory from blue to blue to blue to blue to blue, I call that the blue name sequence. Just as likewise, you can come up with a white name sequence or anything else. There's 1,000 other ways to do this. Here's my thought to you, and this is really kind of interesting. Let's take this. Nope. Sorry. We're going to go to stuff from desktop. Sorry for the little delay here. Okay, so let's say you take wherever we were before, these things. So a blue node steps once to the left, once to the right, and then spawns further. Meanwhile, red nodes don't even spawn anything in particular. To their right they do, but to their left they spawn a trivial branch. So on some level, if you will, the smallest one is red. The next smallest one are white ones, because white take 2 steps to make an orange branch. Blue ones only take 1 step, and remember that if it only takes 1 step to the left and then it spawns more stuff, that means when you're checking, well, how many dots do we have up to a certain value of n, there's going to be more dots in your conversation because it only took 1 step to the left, 1 step to the right, and then branched further. So on some levels, blue nodes create, if you see a lot of blue nodes, you have a larger branch. When you see a lot of white nodes, you have a medium-sized branch, and when you have a lot of red nodes, you've got a small branch. Experimentally, this seems to, my claim is backed up by the experimental evidence. And so I offer you the following thing. When it comes to Collatz branches, actually found in Collatz space, if you're really trying to understand their sizes, it might be more relevant to know their blue name sequence, because it immediately tells you a lot more about its size than to actually specifically just know what was the n value that spawned the branch. And in the next part of this page on the website, I'm going to tell you a little more about how to use that fact.